Scientists have made a staggering claim about 6 remote volcanoes in Alaska, and if they are right, the geological map of North America has to be rewritten. For over 2 centuries, we thought they were 6 separate mountains, 6 individual peaks of ice and rock, piercing the fog of the Bering Sea. But a handful of researchers now believe this is a disguise, a spectacular act of geological camouflage, hiding a single, unified, colossal magma chamber underneath. They believe these 6 volcanoes are just the vents on the rim of a 20-kilometer-wide caldera, a supervolcano. And if the evidence is correct, it has been hiding there, in plain sight, for 166,000 years. The problem is, this system is not ancient history. One of its vents, Mount Cleveland, is among the most active and explosive volcanoes on the continent. It erupts constantly, and just weeks ago, in June of 2026, it woke up again, shaking the islands with hundreds of earthquakes. That activity has quieted. For now. So the real question is, did scientists just discover a geological phantom, or did they just stumble upon the second Yellowstone? An Alaskan monster that we never even knew was there. The islands of the 4 mountains were never supposed to be understood. They were meant to be survived. This archipelago sits in the central Aleutian Islands, a 1,000-mile-long scar where the Pacific Plate grinds itself to death beneath North America. The weather is some of the most violent on Earth. The ocean is unforgiving. For centuries, this was a place that defied maps, a blank space between continents known more for shipwrecks than for science. Early Russian explorers venturing east from Siberia in the 1700s charted what they could see through the perpetual mist. They named the cluster Ostrova Chitaya Sapochnia, the Islands of 4 Mountains. It was a simple, observational name, and it was wrong from the start. There are not 4 volcanoes here. There are 6. Carlisle, Cleveland, Herbert, Kagamil, Tana, and Uliaga. 6 distinct, steep-sided stratovolcanoes spread across 5 islands. But the name stuck, a historical error baked into the geography itself. For over a century, that was the extent of our knowledge. In 1894, a U.S. Coast and Geodetic Survey team arrived, charged with bringing order to this chaotic frontier. Following tradition, they renamed the most prominent, most active peak after the sitting president. Mount Cleveland. They measured its height at 5,675 feet. They marked its position, 947 miles southwest of Anchorage. They cataloged it as just another link in the long Aleutian chain. A solitary mountain on a remote island. No one suspected it was part of something bigger. How could they? The evidence was buried, hidden beneath hundreds of feet of raging, opaque seawater. The islands held their secret through the turn of the century, through the dawn of modern geology. They even held it through a world war. In 1944, as the brutal Aleutian campaign raged against Imperial Japan, the U.S. military established a tiny 5-man army outpost on the island of Chujinadak, directly in the shadow of Mount Cleveland. The soldiers nicknamed it Jinx Island. The name was prophetic. That June, the volcano erupted. It was a Ve3 event, significant, but not catastrophic. But for one soldier who walked too close to the active vent, it was fatal. A sudden mudslide, unleashed by the erupting peak, swept him away. It remains the only confirmed, direct volcano-related death in Alaska's modern history. The military abandoned the outpost. The island returned to its silence, keeping its geologic identity locked away. For another 70 years, the 6 volcanoes were just 6 volcanoes, independent, isolated, and profoundly misunderstood. The story should have ended there, but science is a process of asking questions that get better over time. In 2014, a team of researchers led by volcanologist Diana Roman from the Carnegie Institution for Science traveled to the islands of the 4 mountains. They were not looking for a supervolcano. Their mission was far more modest, focused on archaeology and the rock chemistry of Mount Cleveland. But what they found made no sense. The rock deposits they sampled from different islands, supposedly from different volcanoes separated by miles of open ocean, showed uncanny chemical links. The gas emissions, particularly the high sustained output of sulfur dioxide from Cleveland, were more typical of a much larger, more complex system than a single stratovolcano. It was a geological whisper, a thread that didn't fit the established story. And then there was the map. When you look at the 6 volcanoes on a chart, Carlisle, Cleveland, Herbert, Kagamil, Tana, Uliaga, they are not scattered randomly. They form a ring, a distinct semicircular alignment approximately 20 kilometers or 12 miles across. Stratovolcanoes in a subduction zone like the Aleutians are not supposed to do that. They are supposed to be solitary cones, each fed by its own modest magma plumbing. A ring of volcanoes suggests something else entirely. It suggests they are all connected to a single, much larger feature, a feature that has collapsed. A caldera. This is where the search began in earnest. John Power, a geophysicist with the USGS and the Alaska Volcano Observatory, joined Diana Roman in a hunt for more evidence. They started, as Roman famously put it, by scraping under the couch cushions for data. The region is so remote, so hostile to scientific instruments, that direct evidence was almost non-existent. They pulled together decades-old gravity surveys. And when they processed the data, they found an anomaly, a subtle patch of lower gravity readings right in the center of that volcanic ring. That kind of gravity signature is a classic tell for large calderas, where lighter, less dense rock has filled in the space of a collapsed magma chamber. The evidence was piling up. It was circumstantial, but it was consistent. The final piece of the puzzle lay where no one had ever been able to look properly. The seafloor. Using modern bathymetric mapping, which uses sonar to paint a picture of the ocean bottom, they scanned the center of the volcanic ring. And there it was, hidden beneath the waves, an arc-shaped, shallow depression. A dip in the seafloor, 130 meters deep, or 426 feet, that perfectly matched the curve of the volcanoes standing above the water. It was the unmistakable scar of a collapse, the remnant of a caldera rim. All the clues pointed to one unavoidable conclusion. The islands of the 4 mountains were not islands with volcanoes on them. They were the tips of a single, gigantic volcano, one that had erupted so violently in its past that its center had caved in, forming a massive hidden crater that the ocean had since reclaimed. A sleeping giant. On December 7, 2020, John Power and Diana Roman presented their findings to the world at the American Geophysical Union Fall meeting. The reaction was immediate. If their hypothesis was correct, this newly identified caldera would fall into the same category of explosivity as the Yellowstone caldera, or the Long Valley caldera in California. These are not just volcanoes. They are geologic engines with the demonstrated power to affect the entire planet. But a hypothesis, no matter how compelling, is not proof. The ring of peaks, the gravity data, the seafloor depression, it was all powerful, indirect evidence. To prove it, they needed to see inside. They needed to give the volcano a CAT scan. The plan was audacious. The execution was nearly impossible. The only way to truly map a magma chamber kilometers beneath the Earth's surface is with seismology. By placing a network of ultra-sensitive seismometers across the islands, scientists can record the tiny vibrations from local earthquakes. The way those seismic waves travel, how they speed up, slow down, or bounce off different materials, allows geophysicists to build a 3D image of the crust, to see the shape, size, and depth of the liquid rock hidden below. In 2022, Diana Roman led the expedition back to the islands to do just that. They needed to deploy 8 temporary seismic stations, filed under the network code 3E, across the hostile, uninhabited archipelago. The logistics were a nightmare. The team had to navigate the notoriously brutal Aleutian weather, a region where hurricane-force winds are a regular occurrence. They rode out one such storm, hunkered down while nature threw its full force at their mission. They were helicoptering heavy, delicate, expensive equipment onto icy, volcanic slopes, digging into the permafrost, and anchoring instruments that needed to function for 2 years in one of the world's harshest environments. Every station was a small victory against the elements, a triumph of planning and sheer grit. They were threading a scientific needle, placing sensors with just enough precision to create a seismic net that could capture the caldera's full structure. The goal was to definitively answer the question, is there one giant shared magma reservoir connecting all 6 volcanic vents? Or are they truly separate systems that just happen to look connected? For 2 years, from 2022 to 2024, those 8 silent sentinels listened. They recorded every tremor, every subterranean whisper, every shiver from Mount Cleveland's restless plumbing. The physical deployment officially wrapped up in 2024. The data was collected. It was a technical success. The immense and precious dataset is now in the hands of scientists. As we speak, they are processing it. They are running the models, connecting the dots, and slowly, painstakingly, developing the first ever high-resolution image of what lies beneath the islands of the Four Mountains. We have taken the picture. We are just waiting for it to develop. The answer is coming. What does it mean if they are right? Why does a hidden caldera in a remote corner of Alaska matter to anyone outside of the Alaska Volcano Observatory? To understand the stakes, you have to look next door. Just one island group to the east sits Okmok Volcano. Okmok is also a large caldera, smaller than the one proposed at Itham, but still enormous. In the year 43 BCE, Okmok exploded in a colossal eruption. For years, historians knew of a period of mysterious, unseasonably cold weather that plagued the Mediterranean around that exact time. Roman texts describe dim skies, failed harvests, and widespread famine. The consequences were world-changing. The agricultural crisis in Egypt, the breadbasket of Rome, is now seen by many historians as a key factor that destabilized the Roman Republic, accelerating its collapse and the rise of the Roman Empire. For 2 millennia, the cause of that climate anomaly was a mystery. Then, scientists analyzing ice cores from the Arctic found a layer of volcanic ash with a unique chemical fingerprint. They matched that fingerprint directly to Okmok. An eruption in Alaska had ejected so much sun-blocking sulfur dioxide into the stratosphere that it had altered the climate on the other side of the planet. It had helped bring down a republic. Now, consider this. The proposed caldera at the islands of the Four Mountains is believed to be significantly larger than Okmok. Its magma chamber is vaster. The potential for a truly massive, climate-altering eruption is therefore greater. And a GU press statement in 2020 put it bluntly: if the researchers' suspicions are correct, the newfound volcanic caldera would belong to the same category of volcanoes as the Yellowstone caldera. This is a term that makes volcanologists uncomfortable. Supervolcano is a media creation, not a scientific classification. Diana Roman herself has said, "You may have noted we put supervolcano in quotes." Volcanologists hate that term. From here on out, we'll use the word caldera. But the label sticks because it communicates the scale of the threat. An eruption from a system of this size is not a local event. It is a planetary one. It wouldn't just be ash falling on Alaska. It would be a veil of aerosols thrown into the upper atmosphere, reflecting sunlight back into space and triggering a volcanic winter. Global temperatures could drop. Growing seasons could fail, not just in one region, but across continents. In our modern, interconnected world, the effects would be catastrophic. Air travel would grind to a halt as jet engines, vulnerable to glassy volcanic ash, would be grounded worldwide. Global supply chains, already proven to be fragile, would shatter. The agricultural collapse that crippled ancient Rome would be replayed on a global scale, threatening food security for billions. John Power of the USGS is quick to temper these fears, stating that this discovery doesn't change the hazards. We're not forecasting something dangerous here. And he is right. The odds of such an eruption happening in our lifetime are incredibly small. Geologically speaking, these events are rare. But the problem with the islands of the Four Mountains is that the system is not quiet. It is not a museum piece. It is alive and kicking. Mount Cleveland is the restless heart of this hidden system. It is one of the most persistently active volcanoes in all of North America. It does not erupt on a scale of decades or centuries. It erupts on a scale of months and years. Since the turn of the 21st century, it has erupted more than 20 times. These are not minor puffs of steam. Cleveland regularly sends towering plumes of ash 15 to 30,000 feet into the atmosphere, directly into the flight paths of trans-Pacific airliners traveling between Asia and North America. The Alaska Volcano Observatory watches it with a vigilance bordering on obsession, issuing constant alerts to pilots. It is a constant, simmering threat that requires daily management. And that is just the baseline level of activity. Then came June of 2026. In the middle of the month, the seismic network that had been deployed to scan the caldera began to light up. Mount Cleveland was hit with a significant earthquake swarm. Not a handful of tremors, hundreds of them. The ground was shaking constantly. This was the volcano's plumbing system shifting, magma moving, pressure building. The AVO raised its alert levels, warning of the increased potential for a significant explosive eruption. For weeks, geologists watched, holding their breath. Was this the prelude to something bigger? For this newly identified supercaldera system, was this a sign of awakening? As of mid-July 2026, that specific swarm has subsided. The aviation color code has returned to green. The immediate danger has passed. But the event was a stark reminder, a geological wake-up call. The immense heat engine that scientists suspect lies beneath the islands is not dormant. The 166,000-year-old giant is not sleeping peacefully. It is stirring. The earthquakes of June 2026 were a flex of its muscles, a glimpse of the power contained within. Each eruption from Cleveland, no matter how small, is another piece of data, another clue about the behavior of the larger interconnected system. It proves the volcano is dynamic, its magma chambers are active, and the potential for a larger event is not zero. It is a real, quantifiable risk. So where does this leave us? We are in a moment of profound scientific suspense. The existence of a massive, previously unknown caldera in the United States is no longer a fringe theory. It is a robust hypothesis supported by multiple independent lines of evidence. And the final proof, the definitive imaging from that harrowing 2022 expedition, is currently being assembled in laboratories as you read this. We are on the verge of knowing. Very soon, the scientific community will have an answer. The implications of that answer are enormous. If the CAT scan reveals separate, disconnected magma systems, then the story is simply that 6 volcanoes happen to form a coincidental ring. It would be a geological curiosity, but the immediate threat level would remain unchanged, focused solely on the known behavior of Mount Cleveland. It would be a relief. But if the data confirms their suspicions, if the seismic waves reveal a single, vast, shared magma chamber underlying the entire island group, then everything changes. It would mean that North America has a massive, active, and poorly understood caldera system on its hands. It would mean that every small eruption from Mount Cleveland is not an isolated event, but a pressure release from a much larger and more dangerous entity. It would rewrite textbooks. It would redefine the volcanic risk assessment for the entire North Pacific. It would launch a new era of intensive study as scientists scramble to understand the behavior, history, and future of a geologic feature that managed to hide from us for centuries. A feature that is both an incredible scientific discovery and a sobering potential threat. The work of Diana Roman, John Power, and their teams has been a masterpiece of scientific detective work. They took scattered, incomplete clues, a weird rock, a gas anomaly, a bend in the seafloor, and pieced them together into a theory of breathtaking scale. They braved the worst weather on the planet to plant the instruments that could finally prove it. The science is done. The drilling, in a sense, is finished. All we can do now is wait for the results. We stand at a threshold of knowledge, looking at 6 icy peaks in the Bering Sea. Are we seeing 6 mountains?